All right. So the good news is that second round of recording for that video, the previous video, did record. So I'm extremely happy. I thought something was wrong. Now let's continue. So where we left off, we had tried to define what a curl of a vector field is. I did my best. Again, some of the geometric interpretations do come a little bit later. So let's go ahead and look at our example. So here is the vector field that we're given, and we would like to find the curl of that vector field. And we also want to be able to answer the question, is the vector field irrotational? Well, if it is irrotational, then the curl should equal 0. That's what we learned right when we had ended. So this is the way that we perform. So the operation for finding the curl of a vector field, just using a cross product. But nevertheless, this is the step that we're going to look at. And so let's start by labeling M, N, P. So M is that component, and then N, and then P. And then what we're going to have to do is we would have to take the partials of M, N, P with respect to the following variables, right? So I've already done that. I've already taken all of my partials that I need. And from here, what I'm going to be doing is just plugging them in. So the partial of P with respect to Y is going to be plugged in here. Partial of N with respect to, partial of N with respect to Z is going to be plugged in here. So I'm just going to be plugging in. So ready? So this is this curl of F. Go ahead. This curl of F is going to equal the following. So it's going to be 2Z minus 2Z minus, okay, now continuing to plug in, that's going to be 0 minus 0, J. And then 2x minus 2x, K. So we end up with 0I minus 0j plus 0k. We end up with the 0 vector. In other words, the curl of F is just simply equal to 0. So to answer that last question, is the vector field irrotational without rotation? Well, yes, it is. So thus F of x, y, z is irrotational. Okay. Now we're going to use this, a little bit of the work that we did with example 7, and we're going to take a look at example 8. So you notice for the example 8, that is the exact same vector field, only now our goal is to find the potential function of that. Well, wait a minute. How is it that we want to find the potential function when we haven't even determined that it is conservative? So the way the test for conservative vector fields works in space is all based upon the value of the curl. So, assuming that your, M and P have continuous first partial derivatives on some open sphere in space, the vector field, right? This vector field is conservative if and only if your curl is equal to 0. So that is the test for vectors in vector fields in space. If to state is it conservative, you need to find the curl, and if the curl is equal to 0, then you get to make the statement that it is conservative. Okay? You could go through a bunch of partials as well, you know, setting the partials equal to each other and make sure that works. But that is the idea of what we just did in essence. So if the curl is equal to 0, then it is a conservative vector field. Now that we know it is a conservative vector field, the goal is to find that function out there, right? There's some function out there such that the gradient of that function is equal to your vector field. So this problem now looks nearly identical to the problem we did in the previous video, only we have 3 dimensions as opposed to 2. So let's go ahead and start with some statements. So remember, just like in the previous video, so this is M, I'll label M N P. Those are the partials. So the whatever function f out there, if you took the partial with respect to x, you would get 2xy. If you took the partial with respect to y, you would get x squared plus z squared. And if you took the partial with respect to z, you would get 2yz. Okay. So you should start to anticipate now. We are going to need to integrate, since we have the partials, derivatives, we need to integrate to be able to build the function, okay? So we're going to want to integrate 2xy. We're going to want to integrate x squared plus z squared. We're going to want to integrate 2yz. I will state again that you want to integrate with respect to the same variable that you would have taken the partial with respect to, right? So I make that statement because I've just seen the mistakes happen where they're integrating with respect to the wrong variable. Let's go ahead and perform that integration. Each of these is fairly easy. So this is going to be x squared y. Makeup, we've got to use something. We'll just say plus g. Now I'll come back and I'll fill in here in just a second. If we now integrate with respect to y, we're going to get x squared y plus yz squared plus some constant of integration. We'll call it h. Finally, we have yz squared. If we integrate with respect to z, and we'll just say plus, we'll use little k for the constant of integration. I will go ahead and make sure you understand that each of these constants here, these constants that are born from the integration, are themselves functions. Now, since we are in space, they're not functions of 3 variables, but they are functions of 2 variables. So this g would actually be a function of y and z, and this h would be a function of x and z, and this k would be a function of x and y. Now, from here we want to let me go ahead and grab this information. Go to the next page. Okay, because we're not quite done yet. All right, so we still need to use the information from here to make us to form our function. And again, I will, if you don't mind, if you allow me to speak informally, let me show you, and again, I'll speak out loud, like as if I were doing this problem, that you can, if you want to, when I'm going through, I'll start with the first line here. So I don't have an x squared y, so I'll take one of those. I'll go ahead and take that g. I come down to the second equation here. So I already have an x squared y, so I won't take another one. But I don't have a yz squared, so I'll take that. And I'll take that h. Go down to that third line. I already have a yz squared, so I won't take another one. But I will take that k. So you end up with something that looks like x squared y plus yz squared. And then you can just do plus g plus h plus k. And that is fine for our test. If you look that answer up in the back of the book, they're simply going to take all of these constants, and you can think of it as they're going to just put that all in as one constant. So it ends up looking like x squared y plus y z squared plus, and they would probably use a capital K. This is what the back of the book, the answers in the back of the book would look like. And they're doing that, the way they do that is they would take this and set it equal to this, and then you would have g is equal to yz squared h. Then they would take this and set it equal to this, and they would have something like k is equal to xy squared plus h, and then they would say h is just equal to k. So I understand a little bit of mathematical manipulation is all that is, but it's not needed if you were to, you can just leave it as such, okay? The last topic is again a topic that they don't offer a geometric interpretation of. So again, I'm kind of, it comes later, so I'm just going to do my best. But it's the idea of a divergence of a vector field. I'll try to make a few statements here. So the curl of a vector field is just itself a vector field. Now, the divergence is a scalar function of a vector field. Now, divergence, I'll show you the formula that we're going to use. It just uses a dot product. But before I do that, again, if you get 0 when you're finding divergence, we would just simply say the vector field is divergence free. But if I'm you, I'm simply asking what the heck is divergence, and I don't know why they punt on that interpretation, but this is a passage from the book, and I will just read, okay, so that you have at least some understanding of what's happening. So that divergence can be viewed as a type of derivative of a vector field. So in that for vector fields that represent velocities of moving particles, right? So if you got some vector field out there and every vector in there represents velocities, then you can interpret the divergence measures the rate of particle flow per unit volume at a point. I could continue. So in hydrodynamics, if you get, so we're talking about divergence free. So in hydrodynamics, if your vector field is divergence free, it's called incompressible. In electricity, and magnetism, if you have a divergence free vector field, it is called, don't know how to pronounce that. I think I do, but I'm not going to try. So however that is pronounced is what it's called. That's why I get to say things like that, because I don't study electricity and magnetism of vector fields. So, all well. Now, but I do understand divergence in curl, and let's go ahead and you'll see the dot product in just a second, and we'll just do one problem of divergence. So right now what we have to assume is, again, notice how we're labeling M and P again, right? So, but in essence what happens is, what we have to assume is that the vector field that we are looking at, those components have continuous second partial derivatives. So let me see if I can restate that. So if the following is a vector field and M, N, and P have continuous second partial derivatives, then I should have read before I started. I was thinking we were talking about the formula, but under those conditions, if you were to take the divergence of the curl, you would get 0. That's not really what I thought we were talking about. What I thought we were talking about for a second was how do we find the divergence of a vector field? And we do so by just simply making use of the dot product. And again, there's that differential operator that they're making use of. But what it really comes down to is, what is it that you're dotting? Well, you're going to dot the vector field with the there's that gradient differential operator with respect to x, y, and z. The good news is dot products are a little bit easier than cross products. So as you recall, we just take the I component times the I component plus the j times the j, and so forth. So this is actually all that you need. You don't even need to perform the dot. You just need to make a star or highlight what I've boxed in for you there. So let's find the divergence at a particular point in this vector field. So I went ahead and labeled M, N, P, and I want to take the partial of M with respect to x, partial of N with respect to y, partial of P with respect to z. So let me go ahead and then we're going to take the sum of those. So if I were to start with the partial of M with respect to x, well, that's treating y and z as constants. That's going to be 3x squared, y squared, z. Now, if you take the partial of n with respect to y, and there are no y's, that's going to be 0. If you take the partial of p with respect to z, there are no z's, that's going to also be 0. So this here, this is the divergence of your vector field. But we care to consider divergence at the following point. So all that is going to happen is I'm just going to plug in, so with x equaling 2 and y equaling 1 and z equaling -1, I'm just simply plugging those in. So such that the divergence of f of 2, 1, -1, doing a little bit of arithmetic, and I get -12. Okay, so that will conclude chapter 15, section 1, and I'll see you soon.